Hello everyone and welcome to video number 6 in the Transformers course, and specifically the third video in the equivalent circuit. In this video we are going to cover approximate equivalent circuits. Let's start. Let me remind you what we did so far. In video number 4 we covered exact equivalent circuit not referred to any side. What is the problem with this circuit? The ideal transformer increases the complexity of the analysis, so we can use referring. This is what we did in video number 5. In video number 5 we covered exact equivalent circuit referred to the primary or exact equivalent circuit referred to the secondary. But we faced a problem here as well. The magnetizing branch introduces an additional node into the circuit. That one increases the complexity of the analysis without providing a significant benefit. What we are going to do, we are going to use in this video what we call it approximate equivalent circuit. First, approximate equivalent circuit referred to the primary side. What we can see here is the exact equivalent circuit. Now, instead of using the exact equivalent circuit, we will use the first approximate equivalent circuit because it makes the analysis much simpler. Look here, we have the magnetization branch and the no-load current. The no-load current is small enough compared to the load current referred to the primary side or the secondary current referred to the primary side. By other words, the referred secondary current is close enough to the primary current. So rather than dealing with a more complicated exact model, we can move the excitation branch, or we call it the magnetization branch, to the source side. This will reduce the amount of calculation. So the primary impedance and secondary impedance referred to the primary side are in series. And the analysis gives results are very close to the actual transformer performance. This is why in transformer performance calculations such as efficiency and voltage regulation, which will be covered in the upcoming videos, first approximate equivalent circuit is preferred if the data of magnetizing branch is available. If it's not available, we're going to use second approximate equivalent circuit. We can get a much simpler model without sacrificing the accuracy. So how to make the analysis for this circuit? Firstly, we're going to do the referring. R2 dash equals A square R2. What's A? A is the Turner's ratio, equals N1 over N2. And X2 dash equals A square X2. And V2 dash equals AV2. And I2 dash equals 1 over AI2. If Z load is given, Z load dash equals A square Z load. So how to calculate I node? Using Kirchhoff current law here at this node, where I node equals I core plus IM. And because this circuit is simpler rather than the exact equivalent circuit, so I core directly equals V1 over RC. And IM equals V1 over JXM. And using this node, we can calculate I1 now. I1 equals I node plus I2 dash. But how to calculate I2 dash? If Z load is known, so we know Z load dash, so in this case, I2 dash equals V1 over all of these impedance are in series. So R1 plus R2 dash plus R load dash plus JX1 plus X2 dash plus X load dash. So we can calculate I2 dash magnitude and angle. But if Z load is not given, so we can calculate V2 dash. In this case, we are going to use from this loop, this one as well, Kirchhoff voltage law, where V1 equals V2 dash I2 dash Z equivalent. What is Z equivalent in this case? R equivalent plus JX equivalent, which is R1 plus R2 dash plus JX1 plus X2 dash. What about referring to the secondary side? The first approximate equivalent circuit referred to the secondary is as shown in the figure. Any impedance in the primary side will be multiplied by 1 over S squared by the original impedance, and the voltage V1 dash equals 1 over A V1 and I1 dash equals A I1. So how to analyze this circuit? How to solve this circuit? We are going to use Kirchhoff voltage law in this loop, or if we know Z load, we are going to divide V1 dash by all of these impedances are in series. V1 dash equals V2 plus I2 Z equivalent. What is Z equivalent? R1 dash plus R2 plus JX1 dash plus X2. And using Kirchhoff current law at this node, I1 dash equals I node dash plus I2. So how to calculate I node dash? Equals I core dash plus IM dash, and we know that V1 dash is applied directly to the magnetization branch, So I core dash equals V1 dash over R core dash, and Im dash equals V1 dash over JXM dash. So what will be the case if Z load is known? So we are going to take all the impedances are in series. So I2 we can calculate it magnitude and angle equals V1 dash over R1 dash plus R2 plus R load plus J X1 dash plus X2 plus X load. So in this case the circuit is more simple rather than the exact equivalent circuit. Let us take an example. We are going to use the same example we had before in the video number 5, but in this case we are going to solve this example using approximate equivalent circuit instead of exact equivalent circuit. We have a 10 kilovolt ampere 2000/200 volt 50 hertz step down transformer and has the parameters not referred to any side, 4 ohm in the primary and leakage reactance 8 ohm, and in the secondary winding resistance of 0.04 ohm and secondary winding reactance of 0.08 ohm. The equivalent core loss resistance is 20 kilo ohm and magnetizing reactance is 5 kilo ohm. So the transformer is operating at full load with a lagging power factor of 0.8 and the secondary load voltage is adjusted to 200 volt RMS value. So we need the equivalent circuit referred to the primary side. We are going to use the first approximate equivalent circuit and then we are going to calculate the primary voltage and the transformer power factor. We start by the turns ratio, 2000/200 equals 10. So the equivalent circuit referred to the primary side, we have R2 dash, we have X2 dash, and we have V2 dash, in this case equals 2000 and angle 0 degree volt. This is the circuit, approximate equivalent circuit, first approximate equivalent circuit referred to the primary side. And we notice now that R1 and JX1, R2 dash and JX2 dash will be in series. To calculate the primary voltage, we need to calculate the secondary current referred to the primary side, and we know that the transformer is operating at full load, so the current at the secondary side will be S over V2 equals 10,000/200 equals 50 ampere. So the secondary current referred to the primary side equals I2 dash equals 1 over AI2 equals 5 ampere. What is the angle of this current? We know that the transformer is operating at 0.8 lagging power factor, so cosine theta V minus theta I equals 0.8. And we choose the angle of the voltage 0 degrees, so the angle of the current will be minus 36.8 degrees. So in this case, the current I2 dash will be 5, angle minus 36.8 degrees equals 4 minus J3 in the rectangular form. So what about the voltage V1 now? So we can apply Kirchhoff voltage law in this loop. So V1 equals V2 dash plus I2 dash Z equivalent. What is Z equivalent? These impedances are in series. Z equivalent equals R1 plus R2 dash plus JX1 plus X2 dash. In this case, Z equivalent it will be 8 plus J16, 17.89 angle 63.43 degree ohm. So the voltage V1 will be V2 dash plus I2 dash Z equivalent equals 2080.34 angle 1.1 degrees volt. To calculate the transformer power factor, we need to calculate the angle between V1 and I1, and to calculate I1, we need to calculate I node to add it to I2 dash to find I1 magnitude and angle. So the current I core, or the core loss current, will be V1 over R core, and also the magnetizing current IM will be V1 over JXM. Please don't forget the J, the 90 degree for the XM. So in this case, we calculated I core and IM. So I core plus IM gives us I node. So if we add I node, magnitude and angle, or in rectangular form will be real and imaginary, to I2 dash, so in this case I1 equals I node plus I2 dash, that one gives us 5.344 angle minus 39.7 degrees ampere. That one will be I1. But V1 has an angle 1.11, so in this case cosine theta V1 minus theta I1 will be the power factor of the transformer. So in this case cosine 40.8 equals 0.757 lagging. An approximate equivalent circuit referred to the primary side. We can have further simplification to our circuit. If the secondary current referred is big enough with respect to the no-load current, the no-load current can be neglected. Hence, the magnetizing branch can be removed. And the equivalent circuit will be as shown in the figure. Just the primary impedance and the referred secondary impedance are in series. So that one will be as shown in the figure now. R equivalent and X equivalent. So we can apply directly Kirchhoff voltage law, and in this case, I1 equals I2 dash. Z load dash equals A square Z load, and all the impedance referred from the secondary to the primary will be multiplied by S square. V2 dash equals AV2, I2 dash equals 1 over AI2, and I1 equals I2 dash. R equivalent equals R1 plus R2 dash. X equivalent equals X1 plus X2 dash. As a calculation, I2 dash equals V1 over total impedance if we know Z load dash. So V1 over R1 plus R2 dash plus R load dash plus J X1 plus X2 dash plus X load dash. And V1 equals V2 dash plus I2 dash Z equivalent. If we don't know Z load dash, we can use this equation. Regarding the referring to the secondary side, the equivalent circuit will be as shown in the figure, where R1 dash and X1 dash will be in series with R2 and X2. And in this case, I1 dash equals I2. So the equivalent circuit can be redrawn as shown in the figure, where we have R equivalent and X equivalent. So the values can be calculated using these equations, where R equivalent equals R1 dash plus R2 and X equivalent equals X1 dash plus X2. If we know the load impedance, so we can calculate I1 dash, which equals I2 equals V1 dash over all the impedances are in series, R1 dash plus R2 plus R load plus J X1 dash plus X2 plus X load. If we didn't know the load impedance and we know the secondary voltage or load voltage V2, we can use Kirchhoff voltage law equation, where V1 dash equals V2 plus I2 Z equivalent, and Z equivalent in this case equals R equivalent plus JX equivalent. Let us take an example. We are going to repeat the previous example, but this time we are going to ignore the magnetizing branch. So the second approximate equivalent circuit will be as shown in the figure. We have R1 and X1, R2 dash and X2 dash. The voltage, secondary voltage referred to the primary side, will be 2000 and angle 0 volt. Like the previous example, to calculate the primary voltage, we need to calculate the secondary current at full load, which is 50 ampere. And the secondary current referred to the primary side is 5 ampere. We are going to calculate the angle of the secondary current referred to the primary side. So that one will be minus 36.8 degrees. I2 dash equals 5 angle minus 36.8 degrees equals 4 minus J3 ampere. So V1 equals V2 dash plus I2 dash Z equivalent, which is identical to the first approximate equivalent circuit. And in this case, Z equivalent equals 8 plus J16 or 17.89 angle 63.43 degree ohm in the polar form. So V1 equals V2 dash plus I2 dash Z equivalent, which equals 2080.34 and angle 1.1 degrees volt. And that one is identical to the value we had in the first approximate equivalent circuit. What about the power factor? So the power factor is cosine the angle between the primary current and primary voltage. So in this case, we have cosine theta V1 minus theta I1, and I1 in this case equals I2 dash, so cosine 37.9 equals 0.789 lagging. Now we solve the same transformer problem using all the three equivalent circuit models. Let's compare the results. Starting with the exact equivalent circuit, we get the most accurate representation because every transformer parameter is included in the model. This is typically the approach used in software-based analysis and simulations, where computational complexity is not a major concern. When we move to the first approximate equivalent circuit, where the magnetizing branch is shifted to the source side, we will notice that the results are almost identical to the exact model. Look for the primary voltage here. So for the exact equivalent circuit, we have 2084 volt, while in first approximate equivalent circuit, we have 2080 volt. For the primary current, we have here 5.337 ampere, while here we have 5.334 ampere. So they are identical. For the power factor, 0.757 and 0.757 lagging. So the primary voltage, primary current and power factor show only very small differences. This tells us that the approximation is quite good and allows us to simplify the calculation significantly without losing much accuracy. When the magnetizing branch is completely neglected, the circuit becomes even simpler, and the results are still reasonably, although we can now see a small difference in the primary current and power factor. Look here for the first approximate equivalent circuit, we have the current 5.334 ampere, while in the second approximate equivalent circuit we have the secondary current, which is 5 ampere. And the power factor here is 0.757 lagging, while here in the second approximate equivalent circuit is 0.789 lagging. Even so, for many practical calculation, this level of accuracy is often sufficient. efficient. So the main conclusion here is that there is always a balance between accuracy and simplicity. The exact equivalent circuit gives the highest accuracy and is well suited for simulation tools such as MATLAB. However, for manual calculation, design work, and exam problems, the approximate equivalent circuits are often preferred because they reduce the complexity of the analysis while still producing results that are very close to the exact solution. As these results demonstrate, a well-chosen approximation can save a lot of effort while maintaining a high level of engineering accuracy. So after we covered the approximate equivalent circuit, we are ready to cover the transformer performance. So what will I watch in video number 7? In video number 7, we are going to cover transformer efficiency. See you in the next video.